Okay, so today we will start with the actual content of the course. So the first 2 days are more mathematics, and the second the last 3 days will be more about biology. So yeah, today it is a little bit more mathematical part of the thing. You may remember system biology is a kind of mixture between 3 different things. One is biology, the other one is the technology used to measure the biology. The other one are the models and the mathematical models of these 2 things. So we will start with the mathematical models. So lecture 1 is about biological systems, and we mentioned last time that systems biology is very much about networks. So a network is an agent, is a collection of agents that interact with each other, and they may interact at different levels. So you may have molecular networks, and then the agents are molecules, and they interact with each other. Or you may have cellular networks, and then the cells interact with each other. Or you may have organ networks. All these make a person, and people also interact with each other in social networks and in population. Contando un chiste, anda. Okay, so networks are very important, and at the level that we will see systems biology will be mostly at this level where we have protein networks, molecules networks. We will not see so much cellular networks, but they all behave the same, and the kind of models that are used are the same for all of them, for all the networks. So yeah, so here you are familiar with this kind of networks where you have a cell, and then this cell has receptors in the membrane, and then these receptors sense some molecules that are arriving, so some I don't know, survival factors, chemokines, hormones, whatever. And then once they are detected, there is some conformational change in this protein, and then this conformational change causes some interaction with some other proteins, and then there is a whole interaction network that transfer this information from here to wherever in the cell. So this is the kind of networks we will mostly see. But there are also other kind of networks. So for instance, this is an ecological interaction network between different species in some sea. And the kind of equations that we will write for molecules are the same as the ones that we need for this kind of networks. So when you start modeling, first you have to decide which is the problem that you want to solve. So which is the problem or the network that you want to understand. You will make some assumptions. We will see examples later. You will define some variables that you will be able to measure, or will be internal variables, and these internal variables will transfer to an external variable that you are able to measure. And then there will be some approximation, because you have some observed data, and then you have to feed your model to the observed data, and then you get some results. Okay, so here is an example. So here is a very simple network. There are only four molecules here that are interacting. So there are 3 latent variables that are kind of internal variables of the cell. This is a very, very simple molecule network, if you will. And there are 2 external inputs. So one of them is the input. So this is, you may think of this as a very simplified model. Okay, so you may think of this as a very simplified model of this network that we were drawing here in the cell. So there is an external input, and then this external input acts on some molecules and information is transferred. So this would be the input, and then the first molecule detecting it is X, and then it transfers the information to Y, and then it transfers the information to Z. And there is an enzyme here that is also acting on some of the reactions. And then here is the model. So this is the kind of models that we will write. So there is this is the derivative of X. So the change in X over time is a function of the input. U is the input minus some coefficient times E X to 0.5 power. Okay, and why this? Because this E and X bind, and then they both produce Y. So when they bind, what is the probability of binding? The probability of binding depends on the amount of E. So the larger the E, the more, the higher the probability, and the amount of X. But this depends on, so that is why we need both. The higher the two, the larger the probability of interaction, and that makes this this product to be larger. And the relationship with E and X may be nonlinear, so not all the powers involved need to be 1. So here in our example, one of them is 0.5, can be whatever. And then when they bind, they produce Y. So if they produce Y, then X disappears because it has been converted into Y. And then the change of X decreases. Okay, so that is why we have a minus sign here. So the input produces X, so the higher the input, the larger the X, but then X binds E to produce Y. So X decreases, but Y increases by the same amount. So whatever disappears here, appears here. And then Y is the same, so the change of Y over time is whatever is coming from X. So this is a positive contribution, minus B, so some coefficient, and Y decays into Z, so, and it decays at this rate. So it disappears from Y, but it appears in Z. And then the change of Z over time is whatever is coming from Y, and then Z also disappears. Okay, so it is changed into, or it is excreted by the cell or whatever. Okay, so this pattern, that there are two important patterns here. So one is that a negative sign in one is a positive sign in the other one, in the next one. Okay, so whatever disappears from X has to appear in Y. Whatever disappears from Y has to appear in Z. Okay, and the other pattern is this probability of binding. So whenever there are two molecules that are interacting, typically this is modeled in this way. So the higher E and the higher X result into a higher probability of binding. Okay, so these are differential equations. So we have to solve those differential equations. So what we will do is to use some numerical method. Okay, so in general, this kind of equation systems, you can write as, okay, so I'll use the, how to, so okay, so we have something like this. Okay, I will write it only for a couple of them. Yeah. No. So we have X derivative, and it is equal to, I don't know. I will skip the. I will not skip the input. So minus A. EX 0.5. We'll write only the first two. And then Y was A x 0.5 minus some g y 0.5. Okay, so now I can write a vector. I would like to have a thinner vector. So yeah, let us see like this. Okay, so I will write a vector x, y, and this is, yeah, I am omitting the time dependence, but there is a time dependence, and this is a vector. This is a vector that we will call the state vector. Okay, so this is my state vector. So I can rewrite now. This equation in a different way. So let's make this. Yeah, so this is the state vector. So what this is saying is that the derivative of the state vector, and now I am omitting t, we don't need it anymore, is equal to what? Is equal to, okay, so all this part is a function of s. This is a function of s. So this will be a function of s. What else have I used? Okay. Yeah. So this is a function of s. And then plus another function from the inputs. Okay. And this is a vector, so this has to be a vector. This has to be a vector, and this has to be a vector. And this is a differential equation. Okay, so the change of the state over time is a function of the state and the input. Okay. And this is change over time. Change over time. Okay, so in general, if we want to solve an equation system, so what we can do, let me go back here. So this is our equation system. Here I have omitted, for simplicity, I have omitted the part depending on the input. Let us concentrate this part, the one that does not depend on the input is called the homogeneous equation system. Okay, so let's concentrate on the homogeneous part. And in the homogeneous part, we will have to solve this. Okay, so this Euler explicit method, have you seen it?
Yes.
Yes. Okay, so I don't have to explain it. Okay, so what says is that the next state will be the current state plus some time step times the derivative of s, but at the current time. Okay, so this is the time we know, and this is the time that we want. This is the state, the next state that we want to compute. Okay, and this time step is typically called h, and then this derivative is this one. It's this one evaluated at the time tj. Okay, so that's what it's saying is if this is time, this is my state, and I know that currently I am at this point, so at tj I am in this state. This equation here, what it's saying is that you can approximate the curve by a line, by a straight line. So that is why this is the equation of a line. So you have, this is the intercept, and then the time step, and then the slope. This is the slope. Okay. So what we will do is to approximate, if you take this h small enough, then the curve, the two curves, that is the green one and the red line, are sufficiently close. So that is a good approximation. That is a good approximation if the time step is small. Okay, so here you see something that is, this is my encoding of the slides. So when the URL is below, is that it is something I have taken this from here, and also it is interesting for you to explore. So later, for instance, when you are doing your own research, you may want to go to here to understand better the Euler method. Okay, so yeah, this is fine in the equation, but we have to simulate it. So to simulate it, this is very simple. So what we can do is, okay, so let's say that I want to solve an equation. I don't see the equation here, but okay. So the equation is here. So f is the exponential of minus t. So what we are doing is solving this equation. Okay, so we are solving this equation. So y of t, the derivative is minus exponential of minus t. Was it minus t or t? Minus t. Okay. So this is a equation that we want to solve, and we want to solve it for y. Okay, so we want to find y that satisfies that. Okay, so this one. It's confusing having two computers at the same time. So this is our f. This is our time step. This is we will solve the equation between 0 and 1. Okay, so this is the way of saying Python to create an array between 0 and 1 in the steps of age. This is our initial condition. This is, you may remember from differential equations. So it is important that when you specify the equation, you also specify that there were two kinds of solutions for this. So first solution was the general equation, and the general solution. And the general solution had some free parameters, and then you also have the particular solution. And for the particular solution, you had to give the solution at 0, the initial condition. This is called initial condition. So you have to say what is the value at the beginning, and then by saying what is the value at the beginning, you can iterate. Here. So you need s of 0. Okay, what is my first state? And then you let it evolve. So yeah, so we have the initial condition, and now yeah, so here the solution is called S, it's not called Y. So S will start with a lot of zeros. The first sample will be the initial condition, and then we loop over all time steps. For each one of these time steps, we take the current state, multiply by the time step, and then evaluate the slope at that point. And the evaluation of the slope is this one. And then you keep on iterating, and then we will plot it. Okay, what if you use, we are solving the equation between 0 and 1. The green curve is the exact equation, the exact solution, and this time step 0.1 is going from 0 to 0.1, 0.2, 0.3, and you see that at the beginning it is close, but then we are approximating the curve by a line. So this approximation, the farther you go, the less good it will be. So that means that the farther you go, more errors will accumulate, and they may eventually become irreversible. So if you make the time step much smaller, now the approximate, so the numerical solution and the exact solution are much more similar. Okay, so this is Euler explicit one. Okay, Euler explicit method to solve differential equations. Okay, what about, is it the most used one? It is not. And actually, you can program it yourself, but typically you use some method programmed by somebody else. And one of the most used is this Runge-Kutta 4.5. And you see that the spirit is the same. So that is a time step. The time step is still h. And the next state will be the current state plus something that depends on h. And this dependence is through these values k1, k2, k3. Here you have all these values. And then you have also ch, and ch are some coefficients. So these coefficients here, this is ch1. So ch1 is this one. So it is a given number times k1. And k1 is h times the slope evaluated at this point, and a1 is another constant, that is this one. So it is rather cumbersome, but you can do it, so the program can do it. So what is the advantage of Runge-Kutta with respect to Euler? Euler is very simple. Why don't we use Euler?
Because maybe depending on the state that you choose, you are going to obtain something that is more approximated or not.
Yeah. So the key is in this approximation. So when you are making this approximation here, so when you say the derivative is approximately, so this from here to there, this is continuous, this is discrete. So in this discretization, what you're saying is the derivative is approximately the slope at this point. This is another way of rewriting this. And you will have some error. So I will rewrite that. So this is not what I want. What I want is this. This is something that you have seen in numerical methods. So, sorry. So in numerical methods, you have seen, okay, so we have this one. Okay, so you have derivative of s with respect to time is equal to f of s. Okay, this is continuous. Now I'll make it discrete. Okay, so if I make it discrete, what I have to say is derivative of t plus h minus st divided by h is approximately at the time tj. So this is at a particular time. This is approximately this one at tj. Approximate. So that means that there is an error. So there is an error. So the error in Euler, is much bigger than the error of Runge-Kutta. So that is why you may prefer some methods to others. Okay, good. So then here, let's go back to here. Okay, so Runge-Kutta, you don't have to program it. We use SciPy. Have you encountered SciPy before? Yeah. Okay, so you know it is a numerical library in Python, and it has a function called ODEINT. So ODEINT is the integration of this differential equation. And the default method, I think it is this Runge-Kutta. That is why I mentioned that before. But still, you have many other parameters there that you may control, and if you want to know what they mean, you have to go to the documentation and see. Okay, so let's solve our example. So we have this equation system, And this is now the full equation, so the non-homogeneous one. This is the homogeneous part that depends only on itself, and then on the input. And then we will see the code now, but what we will have is an input, a u, that is a step function. And this step function starts at 1, and then it will translate into x, and then x decays into y, and y decays into z. Okay, so here are the different curves. So at the beginning, because the input is going from low to high, then x will also from low to high. So it was 0, and then it starts growing. And at some moment, the input disappears, and because it disappears, there is no extra positive income into x. So all it can do is just decay into y. So that is why once the input disappears, now x starts decaying. And y, what about y? So as soon as x starts growing, y will also start to grow. And when x peaks, still y will keep on growing a little bit, but then at some point x starts decaying. So there is no more encounters between e and x because the x is going low. So the income into y will also start to grow low, to go down, and then y is decaying into z. So at some point y will reach its peak, and then it will go down, and the same for z. Okay, so these are the concentrations of these molecules, predicted concentrations of these molecules inside this cell. Okay, so let's look at the code. So the code should be here, and here we have it. So this is what we. This is a notebook, but Jupyter notebook. Some text describing what we are doing. I have taken this from this example, and then in imports and libraries, we define what is the time range for which we will simulate our stuff. Then we define U. U is the external input. So the external input will depend on T, but also will depend at which time it goes up. So it goes up at T0, and it will disappear at T0 plus tau. And the value that we'll have when it is up, it is U0. Okay, and so this is just the step function. Okay, so now we can plot the step function just to make sure that it works correctly. So this is what we get. And then we have to define constants for our parameters. So these parameters A, B, C, and E will take some values. Okay, so these are the values. And now I have to define the F. The F is the slope. Okay, it will receive the state, the time that we want to compute, and then all the parameters that it needs. So it needs A, B, C, E, the U function, that is the input, the arguments of U. So this is just Python stuff. And then we compute U at that time. We unpack the state into its 3 components. We compute the derivatives for each one of the components. So this was minus A times E plus power. And then this is the derivative of Y, and this is the derivative of Z. And the output is F plus U. So it is the internal derivative plus the output derivative. Plus, not the output derivative, plus the input. Okay, our initial state, 0. And now we solve the differential equation. So we solve it with this function from SciPy. And now at this point, we have the solution of S. And the solution of S is the one that I have shown before. Okay, so for the course, you may remember there was one point that was my own work, but real work like this one. Okay, so whenever you are interested in any one of the models that we are writing, you may implement it and give examples and show for what they can be useful. Okay, so the last point of the evaluation is writing this kind of stuff or even more sophisticated. Okay, so this is very basic stuff. Okay, good. Okay, so now we were saying modeling. So this is an outline of the kind of stuff we have to do. So we have to define our goals. We have to select the model that we want to write. So I have shown you now differential equations as a model, but they are not the only ones. Then you have to design your equations and your model. Then you have to fit it and see how it works. And then at the end, you will use it. Okay, so we will see each one of these steps in more detail. So the first one is what about the model itself? So which is the scope of the model, what we want to do with the model, and which are the data that we have available, what other information we have available about how that world works, and yeah, so whether the model is feasible, whether it is interesting for the community, and so on. Okay, so let's start with the model selection. So for the model selection, we have to fix the structure of the model, and one of the first things we have to say is whether we want an explanatory model or a correlative model. And we will see an example in a moment, whether our model is static or it is dynamic. For instance, differential equations, they are dynamic systems. They're also called dynamic systems because they show you how things evolve over time. You have to decide whether you want to use continuous or discrete variables, whether your model is deterministic or stochastic. And yeah, so you have to take many decisions. Open and close, yeah, all the others are also important. So spatially distributed or spatially homogeneous. So spatially, does the model depend on space or not? Open versus closed. An open system receives inputs from the external world and produces outputs, while a closed system doesn't interact with anyone outside itself. Approximations. And here is an example of a correlative model or an explanatory model. So correlative model is, let's say that you have this experiment where you throw a couple of balls from the Pisa Tower and you try to measure the time it takes to go from the top of the tower to the ground. And so our model will be the height will depend on time, and will depend on time in that way. So I will start at the top of the tower. So I will start this. A will be the top of the height of the tower, and then the height goes from whatever it is to 0. And it goes to 0 in this way. And then B will be that number. And why that number? You may remember it is the coefficient here was the half of the gravity constant. And the gravity constant is 9.81. So the half of it is that number. So yeah, so now you have some time. So you put between 0 and 3.5 seconds in the steps, in 100 steps, and now you can compute it. Okay, we'll see it in a moment. And this is a model. I can tell you what is the height as a function of time. But it is not explanatory. So if you change the height of the tower, or you make any other change, we will see a very interesting change later. then I don't know how it will behave. But this one is explanatory. What I'm saying here is the change in height depends on the speed, and the change of speed depends on gravity. So this is a mechanistic model. This is the forces that are acting on that object. So I will define the gravity constant, and then I will define this F, that is the derivative. So the derivative of y is v, that is the velocity, and the derivative of the velocity is minus g. So now the state of the object is defined by two things, the position and the velocity. Okay? And then you have to integrate it, and you get the result. Yeah, here we have the result. Let us go to the code. So go to the code. We go to here. So I will close this one. And we open this one. Okay, so here we are. So this is the correlative model. So for the correlative model, when you go in time from 0 to 3.5 seconds, this is what you have. So you start at the height of, I don't know, 55 meters, and then it will go down this way. Okay, so this is the height as a function of time. So it is not that you throw it to the front. Okay, so it is going down, and this is the height as a function of time. Okay, at which time does it hit the ground? This way. Okay, good. But this, if I change anything in the system, I don't know how that will translate into this equation. I don't know. What about the explanatory model? So the explanatory model we have already seen, and these points, these orange points are the correlative, so it is just the one above, and this is the explanatory. So the explanatory is totally consistent with the other one that it should, and it gives you the same solution, but now it gives you the explanation. So there are forces that are acting on an object, and the state of the object is defined by the location and the velocity, and then you know how they change over time. Okay, so now let's include air friction in the model. So if I have to include air friction in this model, I don't know how to put it. I don't know. Okay. If I have an explanatory model, I know how to do it, because it will be another force. So now the velocity is beside going down with the gravity at the acceleration of gravity, we have some other force acting on it, and this force will be given by a number of things. It will be given by what is the density of the fluid, so the density of air. What is the speed? You may know that the fastest you go with in a fluid, the larger the reaction of the fluid, so the larger the friction. And what is the cross-sectional area? So the cross-sectional area is what is the size of the object. So that is why parachutes, they have a very wide cross-section. So that is why you use parachutes to fall down from a plane. And then you have some drag coefficient. That is okay. But now I know how to include that into my model. So mechanistic models tell you what are the mechanisms behind the behavior of the model. And while correlative models, these ones, they may explain some particular situation, but they don't generalize typically. Okay, good. If something is predictable, we may think, okay, so if I have an equation that there is nothing random in it, then I should be able to predict it perfectly over time. Okay, so let's see if that is true. So this equation here is called the logistic equation. So the logistic equation, let's write it here, because I think it is a little bit small here. So what it says is that the state at time n+1 will be some constant times 1 minus the current state times exactly. Okay, so if you know R and you know the current state, you can predict this forever, right? And you can predict it with infinite precision. Okay, good. So this equation was, it is related, actually, it is related to the growth of populations. We will see it eventually during the course. And yeah, here you have the code to do that. And here you have the predictions for a couple of different constants. Okay, so let's see the code. So let's see this in more details. So here. Let me shut down this. Yeah.
What is the R?
R is a constant that you choose. Okay, so here we have a logistic equation, and this is the code to implement it. I have chosen R equal 3.6, and then we will project forward in time this logistic equation for two different values. One is 0.5. Okay, so this is our initial condition. Our initial condition is 0.5. The other one will be 0.5 plus 10 to the minus 8. So it is extremely, very close to 0.5. So would you think that these two solutions would be very similar? The initial conditions, they are very similar. So we expect that the two evolutions over time, they are also similar. But when we plot them, this is what we see. Okay, that is what you have in the slide too. So at the beginning, they are similar. But at some point, they start deviating. And you see that at some points later, and we are not too far, we are only in sample 240. But so in sample 240, they're already quite different. You may see this goes from 0.3 to 0.9. This plot is not very convenient, so we can make the difference between the two. So we make the difference between the two. At the beginning, they are very similar, but at some point, they start deviating quite a lot from each other. And this starts at around sample 120, and you may see the range there was 0.6, this range is 0.4. So the difference is huge. So this kind of behavior is called chaos. Okay, so chaos is two different initial conditions that are very close to each other. They result into solutions that are very different from each other, even if the initial conditions are exactly the same or almost the same. So this chaotic behavior, many systems have shown this chaotic behavior. And here we have another interesting analysis that is, okay, actually the chaotic behavior of that particular system depends on R. So depending on what is the value of R, it is chaotic or not. So here we are showing for different R values, what are the limit, so whether whether it becomes chaotic or not. So here you see that for values below 3, this is not chaotic at all. So it is totally deterministic. You separate 10 to the minus 8, and they are almost the same. But for values between 3 and 3.4, you have two different kind of solutions. So depending on where you are and what is your initial condition, you may go to one solution or the other. And between 3.4 and 3.5, now you have 4 solutions. And the farther you go to 4, the more possible solutions you have. Interestingly, there are some R values for which there are very few possible solutions. So this chaotic behavior is really something that was discovered in the 60s. And before that, it was thought that if you see this kind of random behavior, it was because there was some stochastic behavior, there was some randomness in it. But here it is not random, it is purely deterministic. But still, you have a behavior that is unpredictable. Okay, so we have described the property of these systems that are chaos. So not all systems are chaotic. We have seen that, for instance, depending on the values, they may be, on the coefficients, they may be chaotic or not. But chaos was a very important discovery because, as I said before, not everything that looks like random is actually random. It can be deterministic. Okay. And next things. So we have shown now deterministic models. So we have shown differential equations or the logistic model. The logistic model. So for instance, here you also see in the logistic, you see the difference between a discrete model and a continuous model. So the differential equation is a continuous model. We have discretized and then solved numerically. But the logistic equation is a discrete, directly discrete. It is not a discretization of anything. It's a discrete model by itself. So that was one of the things that you had to choose. What kind of models you want to have. And another decision is whether you want a deterministic model or a stochastic model. So differential equations and logistic, they are deterministic. If you tell me the values, I can propagate those values over time, more or less accurate, but there is nothing random in there. I can make mistakes, but there is no randomness. But for instance, when we are describing, for instance, molecular species, so molecular species, so let's say that this is the simplest model that we can have. So we have a nitrogen molecule. Nitrogen molecule is made of 2 hydrogen atoms. So we may write the chemical equilibrium in this way. So we can have 2 hydrogen atoms with some constant rate goes to form the molecule, but then the molecule also dissociates into the original 2 atoms. So we can write the differential equation describing this behavior. So we have 2 states, what is the concentration of atoms and what is the concentration of molecules. And then we can write in this way. So we can say for every molecule, let's start with this. For every molecule that dissociates, we will have 2 new atoms. So the differential of H with respect to time will be twice because a molecule results into 2 atoms, and then multiplied by the constant rate. And the constant rate in this direction is K minus. Okay, so if it appears as H, it has to disappear from H2. So this term and this term, now they are not exactly the same. In my previous example, they were exactly the same, but now they are not, because a single molecule of H2 is giving rise to 2 atoms. So here you need a factor 2, here you don't need it. Okay, but the rate of disappearing is the same. So if something, if here it is appearing at this rate, here it is disappearing with a related rate. Okay, and we have the other path. So for the other path, 2 hydrogen atoms have to encounter, they have to bind. So H squared, remember when I was multiplying E times X? So all these encounters where you need a couple of species, they are modeled with a product. So because it is an H, finding an H, it is H squared. And they transform into a molecule at a rate K plus. Okay, and because the molecule is appearing, then we have a positive sign here. But if they have a positive sign here, they have to disappear from the pool of atoms. And the rate at which they disappear is also, again, twice this one, because 2 atoms are disappearing from the pool and they are appearing as a single molecule. So here we will have 2, here we will have 1. Okay, this is a continuous description of these equilibrium. Have you seen these kind of descriptions before in chemistry, right? You haven't seen this? Never? No? Abajo no? You either? None of you? Equilibrium, you have seen equilibrium in chemistry, right?
Reactions.
Reactions. Okay, so this is the description of the 2 species, but this is a continuous description of the molecules. But we know that molecules are discrete things. So something discrete cannot be described in terms of differential things. Either something binds or it doesn't bind. So it is not that at this infinitely small infinitesimal time, then they disappear or appear at these rates. That doesn't make sense for discrete objects. So how can we match these 2 words? Okay. There is okay, let's start with the continuous, and then we will come back to the matching to discrete. Okay, so this equation is true for concentrations expressed in moles. Okay, so this is moles divided by liters. Okay, so let's define our stuff. So we have to define a reaction volume. So a reaction volume will be 100 angstroms. So just for you more or less to have an idea, an atom, a nitrogen atom, is about 1 angstrom of width. So actually I don't remember if it is the radius or the diameter, right? It doesn't matter. It is about 1. Okay, so it doesn't matter if it is 1 or 2. Okay, I think it is radius. Okay, but I'm not sure. Okay, so we define a reaction volume, and we will define it in centimeters cubed. This will be our units. So this volume in centimeters cubed is 10 to the minus 18. Then initial number of H molecules, of H atoms. These are atoms, not molecules. This is H naught. Okay. So at the beginning, we will start with 1,000 atoms. And then we define the 2 constants and the simulation time. And then we define Avogadro's number because we want to express this number of atoms. We want to express it as a molar concentration. So a molar concentration, we have to do it in this way. And then at the beginning, there is no molecule. Okay, all of them are atoms. This is a mistake. This is atoms. Okay, good. Now we have to define the derivatives, but now we know how to do it. So this would be our function f, and we have to say what is the derivative of h, what is the derivative of h2, and this is just the equation, these equations here. And then we solve it, and we plot it. And we will plot it. This is at the level of molecular molar concentration. We have to transfer that molar concentration into number of atoms. Okay, so if to express number of atoms, molar concentration, we take the number of atoms and divide by this. If I want to go back to number of atoms, I have to multiply by the same amount. And this is the simulation. So at the beginning, with these constant rates, we start with 1,000 atoms, and then they start decaying because they start encountering each other, and then they form new molecules. So the number of molecules grow over time, and at some moment they reach an equilibrium. And they reach an equilibrium because the amount of molecules that dissociate is equal to the amount of atoms that associate into a new molecule. Okay, so this is the equilibrium that they have at the end. Okay, we can have a look at the code here. What do I have it here? Okay, so we can have a look at the code. Here it is, and then yeah, so we have seen it already, almost. No, we have seen everything in the slides. Okay, what about the stochastic model? So the stochastic model is, we know that these things are this. We don't have a continuous concentration that goes down in a continuous way. What we have is, if two molecules if two atoms encounter to form a molecule, the concentration goes down by a step. Okay, so they go down in steps. So how can we model that? And to do that, for instance, this is a model used to simulate this kind of reactions. So what we will define is something that is called the probability, the transition probability. So the transition probability is something that depends, for instance, this is the decay. This is the decay, the probability of H2 going to H. This will be K minus, that was the decay constant, times the concentration of molecules. This is not concentration of molecules, this is number of molecules. So now the probability of forming a new molecule, so the probability of forming will be the constant rate times the probability that these two molecules encounter. And again, this probability will be a product between the two, but we have to be careful, because if we choose, we have at the moment we have 8 atoms. So if we have 8 atoms, an atom cannot encounter itself. So it has to encounter any one of the H minus 1 remaining atoms. So it will be H times H minus 1. And then we have to take into account what is the volume and what is the concentration in which that encounters are happening. So somehow this is where the Avogadro's number and the volume enters. Okay, so these are the transition probabilities. So atoms are floating around, and the molecules are also floating around, and the time, just a molecule or just an event has happened. So an event is either two atoms becoming a molecule or a molecule dissociating. So an event has just happened. What is the time until the next event happens? So this time is distributed with an exponential function with this parameter, 1 over the sum of these two probabilities. So the higher the probabilities, the sooner that the next event will happen. Okay, so I can simulate that now. So I can. This kind of simulations, this kind of models, they're called Petri nets. Petri is the name of a guy. Petri networks. Okay, so we take the number of monomers, so the number of atoms, the number of dimers, or the number of molecules. We are at time 0, and then we will keep a list of all the events that happen. So what is the state over time? So at time 0, we had all the atoms were H, and we had zero molecules. Okay, now we compute the transition probabilities. So at this time, the transition probabilities will be, we have them here, so we calculate that. And now we have the transition probabilities. I can simulate what is, I will take a random sample. I will take a random sample from an exponential distribution with this parameter, and just give me a random number. So these exponential distributions, they have this kind of shape, okay? So it's an exponential distribution. So that means that so this is the probability of tau. So this is the distribution function. Remember this distribution function. It was the probability of tau being smaller than a given value. So this is tau, no? And it is something like this. Okay. And what we are subtracting here is an exponential. Actually, I think it is like this. This particular curve is like this. Okay. That is why it is called an exponential. Okay, so I take a random number according to this distribution. This random number will be tau. Okay, so we are at time 0, and after tau, something will happen. Okay, when we are at the end of the simulation, we are done. And then which of the, so there will be an event at tau. Which event? Okay, we have to choose between one of these two. At the beginning, it will be more likely that an encounter between between atoms, because there are very few molecules. So the most frequent event here, the most likely event, should be an encounter of atoms. So we take a random number that goes from 0 to this sum. If it is smaller than W plus, then it is the formation of a molecule. If it is smaller than, if it is larger than W plus, then it is the opposite event. And then we, if it is the formation, there will be one more dimer, and then two of the monomers, they disappear. This is the opposite event. Okay, so if one of the molecules dissociates, there will be two more atoms, and one of the molecules disappear. And we simulate this until we go past the time TF, the final time. We plot it, and this is what we get. Now it is random. And we plot this many times, and what we see is that the continuous model is the average of the discrete events, of the discrete paths. Okay, so the real world is discrete, but the continuous description is the description of the average of what is happening. So what kind of model you want to use? for a particular, for every different problem, it may be different. Okay, more things to wonder when we are modeling. So, which are the dependent variables? Which are the independent variables? What is the kind of processes and interactions that we will model? Which are the signals and the process modulations? What is affecting what? What are the parameters? For instance, in the first model, we have ABC parameters, which are those parameters. And yeah, and how do we estimate those parameters? All this kind of stuff we will have to think. Okay, so here is the same PISA tower problem. So we have measurements of what is time. So at every, let's say that we have a collection of measurements of the height of the balls at different times. So we have a table. We have a table here. This one. We have a table that is at this time HI. So at 0 it was at 55 meters, and then at time, I don't know, 0.5, it is at 40, and at 1 it is at 30, and then we have all this data. Okay, so what is my model? Is my model the height as a function of time? Or is my model time as a function of height? Which one of the two? Or it doesn't matter? Have you studied regression? Yeah? Okay, so the answer is in regression. So it doesn't matter, or we choose one of the two. We have to. Which is? The first one. Okay, why?
Because it depends on time.
Because yeah, but also time depends on age. No? So if my relationship is this one, let's say age is h0 minus 1 half t squared, I can also write this in this way. So I can say twice h naught minus h divided by t square root, this is time. So this is t. So t also depends on age. So I can write both, but not both are correct. And the answer is in regression. Regression and the way you do your experiment. So which is the one that you are more precise? So regression, let's say that this is, I will put it in a generic way. This is x, this is y, this is a function of x. We have some observations. So regression assumes that when you make this line here, it assumes that the error, let's make the errors. Okay. So that the errors are like this. You remember this? This was the assumption of regression. Okay, so that means that y is this plus noise, and there is no noise in the x. X is noise free. So depends on what is your how you do your experiment. So you can do this experiment in two ways. So you can do this experiment in two ways. Can we move it? Okay, so the first way is this one. So I have the tower here. This is my tower. Okay, so now it is straight. And we throw the ball, and I might have sensors at very precise locations, so at 50, 40, 30, and then when it goes down, I measure the time. Okay, so this could be one way. So what is X here? X is the one that I'm more sure about, that it has no errors. Which one of the two doesn't have errors? Height or time? Height. So height here, so let's make the input green. So the height is the one that I'm pretty sure about. Okay, the other possibility is this one. I will make it straight. Anyway, have to give up. No, it doesn't do it. Okay, good. The other possibility is that the sensor is not on the tower, but the sensor is on the ball. Okay, so I have a very precise clock here, and every 1 second, I measure where I am. Okay, so now this is next second, this is next second. So every second, I know exactly where I am. No, I know exactly now, I measure where I am. So now my input is time. Okay? This is my input now. So the one that doesn't have errors is the one that should be the predictor. Okay, so indeed, depends on how you do your experiment. It could be one or the other. Okay, so here we are here. This is what this is saying. Okay, so in least squares, the predictors are assumed not to have errors, so it should be the more precise variable of the two. Okay, what about the model? So we can check, for instance, if there is some internal consistency. So we are dealing with molecules. Molecules don't disappear, so or the mass don't disappear. So if the mass doesn't disappear, so the total mass of the system has to be kept constant. And that's it, for instance, in these differential equations, you might deviate because of your approximation, and the mass may grow or may decrease. An external consistency, for instance, should be close to the data and to the expert opinion. So it should have reasonable steady states. Steady states are those states that are stable. You can do a stability analysis. You can do a sensitivity analysis. We will see these two ideas now. And we can see what are the numerical boundaries and limitations. Yeah. So what kind of states cannot be modeled, this kind of stuff. So what is a stability analysis? So stability analysis is a kind of analysis where you analyze which are the stable states of your system. Okay, so for instance, let's go here. Have you studied in differential equations the phase plane? Okay, so it is an analysis of the phase plane. So let's say that I have a couple of variables, x1 and x2. They both depend on time. So this will be the derivative of x1 with respect to x1, x2. This is my state and time, and this will be the same. And we have seen how we can simulate this kind of stuff, and then I can make a plot of this is x1, this is x2, and this is my first point, this is my first state, x2 of 0. And then, if I let this system evolve, it will evolve over here. It will go down, I don't know. And then it goes to here. Then what I have is a cycle. Okay, so I can analyze Are there cycles in my system? That is one possibility. The other possibility is that the trajectory is different. So the trajectory, you start here, but your system is such that it goes to there. And once it reaches that point, it doesn't go away. So this point is a stable. This point is a stable point. You may not have a stable point, so you may have systems that wander around all the time. You may have cycles. So what kind of behaviors I have? And for that, you have this kind of representations. So you can, if I start here, I will move to there. And then you can make all these arrows here. So you recognize that you have a couple of stable points. This stable point and this stable point. This stable point is actually unstable. So it is unstable because if you move it a little bit, it goes away from there. This is also an unstable point. If you start here, it goes away. Okay. So for instance, let's say I can also describe that there are points that are so there are points in this phase plane. What will happen if I find a point in there? So I find a point in the phase plane. This is my phase plane. And let's call this F. Okay. F is actually the gradient of the state. Okay. So I find a point that is there, such that the gradient at that point, the gradient of the state, at that point is 0. Could be. Okay, so this is not the right notation. The gradient of the state at that point is 0. So if I reach that point, what will happen? It will not move anymore. Okay, so it will not move. But there are stable points that are the gradient. I'm showing here the gradient. Okay, here I'm showing the gradient. So this point here, if I move a little bit away from it, what will happen? We'll go back to the same point. Okay, so this is a stable point. What will happen with this one? If I move it a little bit away from it, what will happen?
It will go away.
It will go away. So this is unstable. So if you are just in the point, you are fine. But these points are called equilibrium points. So this is an unstable equilibrium. This is an stable equilibrium. Okay, so I can describe a pendulum like this. So my description would be the location of this tip and the velocity. Okay, so if I move it to here, it is an equilibrium point, but it is unstable. If I move it away, it will fall down. What will happen if I put it there? This is also an equilibrium point, but if I move it away, it goes back. So this is a stable equilibrium point. This is an unstable equilibrium point. The gradient goes away from it or it goes to it. So you can analyze your system. So once you have defined your differential equations, which are the equilibrium points, and what are the stability of those equilibrium points. This is the other part of the notation. So when you see the link is up, then it is really interesting to go to it. And we do it during the class. So this is a an online version of some equation system. The equation system is a biochemical reactor, and yeah, it is explained somewhere. You have more information about it, so you have here the steady states, and yeah, so you have the description. The interesting thing is that by changing this is the equilibrium, the phase plane, and here we see 3 equilibrium points. This equilibrium point is stable. This equilibrium point is not stable because it could go to this one, and this one is not stable either because it could go away through this line. So if you turn it a bit, these two go away, this kind of behavior, while this one is very stable. And you can think of this also in diseases. So let's say that you have your cell, okay, so or your body, okay, you have your body, and a healthy state is a given concentration of particular molecules, okay, so and if you go away from this equilibrium concentration, it goes back. So this is normally the healthy state. So the healthy state is an equilibrium, this homeostasis. Homeostasis is that if you go a little bit away from it, it goes back to it. So this is homeostasis. When you have some disease, you go away from this equilibrium point and you go to somewhere else. And then you can think, for instance, with protein networks, you can think which is the protein that I can give a drug to it such that the phase plane moves from this state that is a disease state to this other state that is a healthy state. So by blocking one of the proteins, you are acting on these differential equations that we saw before, and then you are moving the stable equilibrium point from one point to the other. The disease state is also stable, so it lasts for some time. Okay, so when I give it a drag, I take it away. So I'm blocking something in my equation system. Then the phase plane changes, and then from this point it will move to this one. But at the beginning, these two were equilibrium points, equilibrium and stable points. Okay, what else? Sensitivity. So sensitivity is the following. And here I have taken this figure from this paper. This for your own research, I think it is very interesting. You can follow this paper and see what they are saying. So let's say that I have a system. And I have to estimate those parameters. I have defined ABC in my first model. So I have said ABC is equal to 0.5. What if I change it a bit? If I change it a bit with ABC equals 0.5, the system has some behavior. What if I change a little bit A? The system changes a lot or not? So if it doesn't change a lot, then it is very stable with respect to A. If it changes a lot, then it is unstable with respect to A. So it is very sensitive. The word is sensitive. So it is very sensitive to A. If you change A a little bit, then the output changes quite a lot. So there are systems that are very robust to changes in the parameters, and there are some other systems that are not robust, or there are systems that are robust to some parameters and not to others, or things like that. Yeah, and if you want to explore more about this idea, you can read this paper if you want. Then maximum likelihood. Have you found maximum likelihood before? Yeah. Okay, so maximum likelihood is I I have some observations. I know that these observations are coming from an stochastic model, so I have some model behind it, so some distribution behind it, and I want to estimate what are the parameters of those of that distribution. So let's say that I have some. Let's look at this one. So here you have a full discussion of this maximum likelihood thing. But let's say that you have some data. Okay, so you have some data. Here it is with some code so that you can try all this kind of stuff. And the one that so let's say that you count how many cells over there. So you take a picture. You take a picture of some blood sample, for instance, and you have many cells, and you count how many neutrophils you have. So here in this example, I have 5. Okay, I take another picture and I count. I have now 2. I take another picture and I count. I have 3. So the number of neutrophils in my picture follows. This is my model. You remember that we have to choose a model. My model is that it follows a Poisson with parameter lambda. And now I wonder, which is the lambda? Which is the lambda? Because sometimes I get 5, sometimes I get 2, sometimes I get 3, but this is expected. This is expected because I know the fact that it follows a Poisson means that if the true value, let's say it is 3.5, I will see no neutrophils with probability 0.05, 1 with probability 0.1, 2 with probability almost 0.2, and so on. So this will be the distribution, the number of neutrophils that I will see. This, if lambda is 3.5. And what is this? This is the probability density function of observing X cells of that kind if lambda is whatever. So what I have to do is, given the numbers, the observations that I have, 2, 3, 5, I have to look for the lambda such that the probability of observing 2, 3, and 5 is maximum. So I can compute the likelihood of observing, can compute what is the likelihood of lambda given my observations. This is the opposite, okay? Actually, this is not equal to this. Okay. But so given this one is given lambda, what is the probability of X? This is the opposite. Given X, what is the probability of lambda? So maximizing this one is called maximum likelihood. Maximizing this one is called maximum a posteriori. Okay. Bayesian statistics. Have you heard of that? Kind of Bayesian models, this kind of stuff. Bayesian is maximize the lambda given the observations. A maximum likelihood is finding the lambda that maximizes the probability of my observation. Okay, so if I have some particular Poisson distribution, the best that you can do is the average. Okay, so the best estimate for lambda is the average. And yeah, you can read in more detail that way, and it describes very well this maximum likelihood thing. Okay, can I always find my parameters? This is something called identifiability. So this is somehow related to sensitivity. Okay, so sensitivity, if a parameter changes a little bit, if it is very sensitive, my system changed a lot. So that parameter is very identifiable because I have my observations. If I change the parameter, it behaves quite differently. So just by playing with my parameter, I can find the one that fits my data. And let's say a parameter is very unsensitive. So that means I change the parameter a lot and then the system doesn't change. So that parameter is not identifiable because it doesn't matter how much you move it, the result will always be the same. So you don't know exactly which one it is. So this identifiability is somehow related to this sensitivity. And here in this paper, they are talking about the identifiability of different parameters in different models. So here you have how a population grow over time. So this kind of population growths, they are very typical in bacteria, for instance. So you have, at the beginning, you have very few bacteria, and you have a petri dish, and you have very few bacteria, and then the number of bacteria multiplies, but at some point, they don't have any more food to eat, so they cannot grow anymore. So they saturate. And so you have these observations of number of individuals in your plate, and you can fit a growth model like this. And you have different models. So for instance, here you may have these Redistic, Gompertz, Richards. Each one of them has different formulations. So for instance, here you have a couple of parameters, R and K. Here you have also R and K, but in a different arrangement. Here you have R and K and beta. So can I identify these things? So for instance, K, this is Logistic, Gompertz, and Richards. This is R. R is very identifiable, but it is very identifiable in Gompertz. So if you change R, it changes so much that you don't have a doubt about what the value is. But for Richards, you don't know which one it is. It is not identifiable. It could be any one of these. And the same here. So for beta in Richards, it is there is very little identifiability. Okay, so the fact that you put a model with some parameters doesn't mean that you have explained how the world behaves, because you may not find the parameters for that. Yeah.
I don't understand what the red lines and the blue lines are.
This red line here,
Yes.
this red line is your estimate. And the blue line is the uncertainty that you have. Could be any one kind of distribution. So it could be any one of these with different probabilities. Okay, so this is the one that maximizes the likelihood, let's say. But all these, okay, the likelihood is not optimal, but it is not too bad. Okay, and why you are using a model? You may want to confirm or validate some hypothesis. So if your hypotheses are true, then this is the model. For instance, in the model of the Pisa Tower, my state my state was defined by the position and velocity, and I had a model how these two things change over time. If my model is correct, then my predictions should be consistent with my observations. And then I may want to use the model to explain the causes and effects. So for instance, in these molecular models, I can tell you what is the path. So X is converted into Y and then it is converted into Z. Or it is the opposite. It is Y is converted into X and then X is converted into Z. I don't know which one it is. So I try to find which of the two competing models is more explanatory. And yeah, I may use, once I have a correct model, I can simulate different scenarios. So I can simulate what is the best case, what is the worst case, what is the most likely case, and how do I change my model, what do I change in my system to change the states. So for instance, this treatment of disease that I showed, I told you before, or in this biomass production that we have, I can try to optimize the biomass or whatever. Okay, so what time is it? Okay, so let's continue. So the last model we will see today is this log-Volterra model. It is a very famous model. So it is these predator-prey cycles. So the idea is that when you have a pair of a species like these two, so when, let's say that you have, at the beginning, you have some number of rabbits and a number of foxes. And at the beginning, for some reason, rabbits start to grow. Okay, so there are more and more and more rabbits. And the number of foxes, so let's say, yeah, this is the reason. So let's say that for some reason, the number of foxes go down for some random thing or whatever. The number of foxes fall down. We will see it is not random. It is related to the cycles. So the number of foxes go down. So if there are fewer foxes, now rabbits grow. The number of rabbits grow because there are fewer predators. But now, as there are more and more rabbits, now foxes have more chances to hunt. And then the population of foxes can grow up because there are there is a lot of food. But then, as the number of foxes go up, they hunt more and more rabbits, and at some time, the number of rabbits start decreasing again. And then, when it reaches the maximum, the number of rabbits, the number of foxes reaches the maximum, the number of rabbits go low, and it may go to a minimum. And then, because there are so few rabbits to eat, the number of foxes again goes down. And it goes down, it goes down. This is the reason why it was going down here. And then it goes down and until you reach a minimum of foxes. And then when you have a minimum of foxes, the number of rabbits go up again. And this kind of predator-prey cycles, or at the end you have cycles there. So this kind of predator-prey cycles appear in many different systems. And again, you have to model this in some way. So you can see this is a very old model. This is going back to the 1920s. So number of the prey population. So the prey population is N and P. This is prey, this is predator. And they are numbers between 0 and 1. Okay, so these numbers will depend on an intrinsic rate of the increase of prey. So there is a natural birth rate. So this natural birth rate, the more rabbits there are, the more rabbits that you have, the higher. Cuéntanos un chiste, anda. Por llegar tarde. Que llega tarde cuenta chiste, si ya lo sabéis. Cuéntanos.
No sé, es que esa no sé los políticos.
Da igual. No te lo sé.
Bandas se caen en medio.
¿Cómo te sabes lo típico?
Pues eso.
Bueno. Okay, so there is an intrinsic rate of birth rate of rabbits, and they have larger the number of rabbits, the more little rabbits they will have. Okay, good. On the other side, these encounters between rabbits and foxes, encounters that are modeled with the product, and the C there will be somehow related to the capture probability. And then foxes will have some per capita mortality rate, so they die naturally. and then so they disappear from the pool of predators. And here, let's see what we have. We have NP, we have CMP. Okay, CMP is the same term that we have there. But then, for every rabbit a fox gets, there will be an efficiency of converting that rabbit into offspring. Okay, it is called assimilation. Okay, so the number of little foxes these foxes will have will depend somehow on the number of rabbits they get, and the number of rabbits is given by this product, CMP. Okay, so for instance, looking at this model, is there any effect that we are not modeling in these two equations? What are we assuming in that model?
No rabbits die of old age.
Yeah, that no rabbit die from age. This term, the only way that rabbits disappear is being hunted by a fox. Okay, so is this a good model? I don't know. It is very famous. And certainly, yeah, it may not represent absolutely everything, but it is a very good model. Here we have a better explanation of it. So if you are interested in this kind of models and where they appear, here it is very much explained. You can run here. So. You can see how the number of predators. Yeah, so you can. And I think you can change also the parameters. Yeah, so here you can change the parameters, so you can change what is the birth rate, and then you can run it and see how sensitive this model is to the different parameters. So you can play a little bit with it. Okay, then, where are we? Here. So, this is similar, this population model, not that was one of the first ones. But this is similar to a population model that is very famous also. Probably you have heard of it in this, during the pandemic, they were talking of the SID model. Did you hear about that, the SID model? It was even in the news. And the reproduction rate of the virus, do you remember that? The reproduction rate? No? Okay, so here again, we have a population model, but now we have three populations. We will have the susceptible population, so those are people who can get the virus. Here we have the infectious population. This is the fraction of people that can infect other people. And the removed population, those are people who have gone the disease and they have recovered or they have died from it. Okay, so but they are removed from the pool, so they are no longer available for a new infection. And this is the SIR model, so it is the first three letters. Okay, so now, how the susceptible change. So the susceptible change because there is an encounter between an infected person and a susceptible one. And there will be a success rate that is this beta. So every time that two people encounter, not always they get infected. So I times S is the probability, is related to the probability of encounter, and then beta is related to the probability that in one encounter they get infected. And they disappear from susceptible and they appear as infectious. So once you get infected, now you're infectious. And you go to remove, okay? So, and you go to remove with another rate, gamma. So this gamma doesn't depend on encounters. So it will take you some time to recover or to die from it, and then you go to the removed removed set. And here you have, for instance, the evolution over time. So let's say that only at the beginning, everyone is susceptible, and then a very, very, very tiny fraction. It is not exactly zero, but it's a very small number of infectious people. Then the number of infectious people grow over time like this, but at some time everyone has recovered, and at some time also what happens, there will be a fraction of people that has not seen the disease ever, okay, because they didn't have any encounter. And this the relationship between, so what is the fraction of recovered, what is the fraction of S, what is the fraction of infectious? Infectious always go to zero, and the other two fractions they depend on beta and gamma. So you can play with beta and gamma, and you can also see how does the number of infectious grow if in a population there is only a single person that is infectious, or there is 100 people, there are 10,000 people. If there are 10,000 people, then the peak of infectious occurs very quickly, very soon, because there are a lot of encounters. If there is only one infectious, it will happen, but it will be quite late, because at the beginning there are very few encounters. And yeah, so you can play a little bit with this model here. So this is the same model that I was showing. Here we have the same kind of equations, and here we have values for those values. And then you can change it, you can change the recovery. So for instance, if you want the why we were isolated, because if you want to, if you move this to zero, this is the transmission rate, then very few people get infected. But if there is a lot of contact, then everyone will get infected. See? More contact. Now the peak will happen very quickly at the beginning. Okay, so more. Yeah, and there I have taken these figures from this article. This is a review of all many different possible models for these infectious diseases. It is a very interesting article. Okay, then this is from, we have seen it there. You need beta and gamma. Which are the beta and gamma for coronavirus? This was the reproduction number that they were reporting in the news. Reproduction number actually is I think it is beta divided by gamma or something like that. So what are the parameters? Because what I see, I don't see these nice curves. What I see is number of infections over time. This was from February 20th. So I see, for instance, in a couple of regions, I see these number of new infections, these number of new infections. This reminds you also of these models of the atoms, hydrogen atoms and hydrogen molecules. So the encounters, they are discrete. So, but these curves that we have seen are the average of different realizations of those discrete simulations. And this is actual data. So the point is, given the actual data, which is the gamma and beta that are more consistent with this data. That was a lot of people working with this stuff by the time of coronavirus.